Hello guys, how are you doing today? Last lecture I introduced the internal forces. It was chapter 7 in our syllabus. I also show you a couple of examples on how do you can calculate those internal forces by using the method of the sections. I hope that you already watched that because that was a really important lecture for understanding the rest of the material. So today we're going to keep working also, but today we are going to be working with shear moment diagrams, and the statics action diagrams are not touched very much, but it's basically the same thing. Shear and moment diagrams, that's but before doing that, also last class I explained you that there are basically three methods, the most commonly used methods: the method of the sections, which is based on what you learned last lecture, and I have several problems that you can practice online also, and then the method of the integrals and the method of the areas. In order for doing this, especially the method of the integrals and the method of the areas, we have to first define what is the relation between the load, the shear, and the moment. And this is the first part of this lecture. This is what I'm going to try to explain you in this lecture. Relation between shear, load, shear, and moment. And this is a very important relation, and this is going to follow you through engineering, and if you are civil or mechanical, aerospace, and you have advanced courses in like a structural analysis course, and even mechanics of material courses, the relation that we're going to derive today is going to follow all the time. In order for deriving this relation, just imagine that you have a beam, and that beam is subject to any type of loading, distributed loading, any type. I'm just putting a distributed load for the derivation. It could be any type of loading, and as you can see, that load W, it varies, it changes with respect to x, and the distance from here to here is L, and x is measured in this direction, for example. So previously, for the method, if this is the support A, for example, and this is the support B, previously, if we want to calculate what is the value of the internal force, and at a point C, for example, here, what we did is that we made a section at that point, and remember, by making a section means that you have to cut this over there like that, and this is the point A with your reactions AY and AX. This is the same function W, and this is the point C, and at the point C, remember, when we do that cut over there, it should appear one shear force. This is the positive convention, and we said this is gonna be the moment at that point. If this point is C, let's call this C, let's call this C, and you're gonna have also an axial force here in C. That's basically what we said last class. Now, what happens if I extract a little portion now of that beam, a little portion like this, let's say a delta x, or let's say a dx, yeah, delta x, a very small distance of that beam. I'm gonna make that detail, I'm gonna make it bigger over here, just for simplicity. I'm gonna put any type of loading here. This is the load, this is the part of the beam, this is the point C, this is the point D, and this is my distributed load, which is W. This is W. It's defined as W, the function W. And remember, when we studied this part here, this is the positive convention, so if we're studying this part here, let's say that at this point B, this distance here also is delta x, and this at this point C here, the positive convention, because we're using this side of the beam, this side, this part, and for D it's gonna be this, but for C it has to be the opposite. So this is gonna be V, this is gonna be M, and I'm gonna not put A, but it should be an A also here in this part, but it's not gonna affect my relation here because I'm using WV and moment. For equilibrium, remember you have to have that force A over there. Now, at this other end, what do you think is gonna happen? And every time that I ask this question, I'm gonna give you 5 seconds. 1, 2, 3. Then here, you should have what? A force also, shear force also V. That's what you're thinking, right? That's for you. You say what it says there? Sorry, brother, that's not it, because this is not V. What? But you just say that this is V, the other one should be V. No, this is not what I said. When you cut at the point, yes, if I study the other side of the beam completely, and this is the point C, and I'm studying the other part here of the beam that continues here, this value here should be VC, and this value here should be MC, and same with the AC. But this is not what is happening here, because here I'm cutting between two parts, so this force V, as you can say, is a vertical force, is affected by also this vertical force here. So let's call this V plus or minus a variation of V. And also with the moment, if this is the moment here, let's call this moment plus or minus a variation of moment. And if we consider the axial, it should be also the axial plus or minus a variation of the axial force. Now, how do we do this thing to work? Okay, our objective is calculating those forces in terms of W, so we can establish that relationship. Let's start from here. Let's say summation of forces in Y equals 0. What is the summation of forces in Y equals 0? Okay, let's start. I have V. Perfect. Minus this force plus the resultant force coming from this load, and what type of load is this? I don't know. What do you think? What type of load is this? Let me give you some hints. What type of load do you think is that? What type of load do you think is that? What type of load do you think is that? That's a Snoopy load. Yay! You know, I started doing this. Snoopy, what is a Snoopy? A Snoopy load. Look at that. You see? That's my type of load, a Snoopy load. You know, I started doing this. The first time that I did this was a long time as a joke. And I kept doing this all the time, and my graduate students now and PhD students and people that see me in the street say, you know something, I might not remember a lot of things from your static class, but I remember your Snoopy load. That's not the idea behind that. But let's say that what I said before I mentioned this Snoopy load here is that this delta x, it was small. So if this delta x is a small delta x, I can assume that this is a rectangular force. Oops, I just trimmed Snoopy nose. This is a rectangular load. I can consider that rectangular load. So here, this resultant force is gonna be W delta x. So plus W delta x, and that has to be equal to 0. Now from here I solve V minus delta V plus W delta x equals 0. This and this cancel out, and then I can say that delta V is going to be equal to W delta x, and I can divide by delta x both sides, and then I have delta V delta x equals W And if I make this delta x really small, basically what I have is that dv is going to be equal to w dx, or I can say also that v is the integral of w dx. And this is a very powerful equation. That equation, what it shows us is that every time that I want to calculate the shear force at any point, I just have to calculate the integral of the function that defines the load on top of that, over that distance. That's a very important equation. Now let's keep going. Now let's work with the second equation. What is the second equation? Let's do summation of moments now. And I'm gonna do summation of moments. Let's do summation of moments with respect to the ear, Snoopy ear, with respect to the point E equals 0. So if I do that, then I'm gonna have V, negative V, times the distance, which is delta x, negative, plus, no, negative also, negative m. Now this one here, this force is negative also, negative w delta x multiplied by the distance from here to here, which if this is a rectangular area, this is going to be delta x divided by 2 because it's half of the base, delta x divided by 2. Yes, now plus the moment, m plus delta m equals 0. And now we solve for this part here. So let's keep working this. And I have this negative m, positive m, cancels out. I'm going to get these two terms passed to the other side. So I'm going to have delta m equals v delta x plus, this is w delta x squared divided by 2. What if I divide both terms by delta x? So if I divide this by delta x, and I divide this by delta x, and I divide this by delta x also, this and this cancel out, this and this cancel out, and I have delta m delta x equals v plus w delta x divided by 2. And if I make that delta x small, what is going to happen is this value is going to be small also, and this is going to become differential, so the m is going to be equal to v dx, and m is going to be equal to the integral of v dx. And the other relation was that the v is the integral of w of x, of course, dx. So these are the two main and one of the most powerful equations that you have in general mechanics. The shear is the integral of the load, and the moment is the second integral of the load, or is the integral of the shear. And you continue after that, because after that you can say, oh, but you have also rotation and you have also deflection, but this is another topic. This is topic for mechanics of materials. Now, how do you apply all of these relations in a problem? Okay, let's do that. I'm going to show you now how to solve a problem by using these relations. And I'm going to do the same problem by following 3 methods. Of course, this is going to be a very simple problem because it's the first problem that we're going to be solving. Let me see, I have a simple problem here. But please pay attention to this one because, as I told you, it's the first problem, but we're going to be solving this problem by 3 methods, and hopefully it's going to help you. You know something? I'm going to record this problem. I'm going to just copy it here, and I'm going to solve it probably in a different video. This force here is how much? 1.5, I think. 1.5 kilonewton per meter. The distance from here to here, this is 2 meters, and this is 2 meters also. And this is the point A, the point B, and this is point C, let's call it like that. And our objective is to draw shear and moment diagram. Remember, shear moment diagrams are drawn because we want to know the value of the internal forces everywhere along that beam. And the best way to go is by doing a shear moment diagram. But I'm gonna solve these in the next video to not to make them too heavy, because they are too long then. Watch the next video, please. See you now.